Welcome to your first example problem for cantilever beams with distributed forces on them. And here we have a very straightforward example. We almost solved it already in the lecture, but let's just complete this here as well, because it helps us to further understand it. And notice that it says determine all support reaction for the cantilever beam with the different forces on them. We have a concentrated force of 10 kilonewton here and 3 kilonewton per meter over a length of 6 meters. And so the first thing that we have to do is draw our free body diagram. So I will pull out my ruler here and draw this rigid body, and rigid body means that it has a dashed line underneath it, which then indicates the positive x and positive y axis. And what often students do is something incorrect that I will erase in a second, but they draw the free body diagram as such. That is not correct because it is not a force indication. You have to bring in the forces, and the forces that you have acting here are actually the vertical force, the horizontal force, and the rotation. So the forces would look something like that. And I just make an assumption here. I assume RAY to go in this direction, RAX in this direction, and MA about the z-axis to rotate clockwise. Now, the forces that act on the structure I also have to include. So I have this distributed force, and then I have the concentrated force as well. So I have 10 kilonewton here, note the units, and I have 3 kilonewton per meter here. And now I can go ahead and solve for my unknowns, which are all in one location, and that will make my job fairly easy. Let's go ahead and do that. So for example, I usually start with RAX, which is calculated by the sum of the forces in the x direction being equal to 0, positive to the right, and 0 is equal to plus RAX. And that is already done because there's nothing else in the horizontal direction. Now for RAY, I take the sum of the forces in the y direction being equal to 0, positive upwards, and 0 is equal to plus RAY minus 3 kilonewton per meter multiplied by, and I should have really done this here in my image, I should indicate that this here is really 6 meters. 6 meters. And so now I can multiply my distributed force by 6 meters. And then I have to include my last force here, which is also going down, therefore it's minus 10 kilonewton. And 3 times 6 is 18 and 10 is 28, so therefore my RAY comes out to be positive 28 kilonewton. This is a result, therefore I have to double underline it and also use my answer arrow. All right, and I can move on to my moment about A. So M about A about the z-axis is calculated by the sum of the moments about point A, and that is counterclockwise positive being equal to 0. And 0 is equal to, I start with my unknown. In this case, it happens to be negative MAZ. And actually, let me rewrite this. I showed this to you before. What I often do, or what I sometimes like to do, is I have double signs. So minus for the rotational sense and then positive MAZ, because it's positive defined, right? This positive stands for, hey, this picture here is always positive, no matter in which direction it points. But this is the directional sense in the definition system here. So now I can use my other forces, which are 3 kilonewton per meter multiplied by 6 meters. And you guessed it, the right lever arm here to use would be 6/2 meters. And don't get confused here. The 6/2, you could think it's going to this side or to that side. I see that being confused sometimes in the classroom. Of course, we take the moments about this point as indicated right here, and therefore the lumped force distance is from here to here, like wherever that center is of this beam. And so the entire force will rotate this way, which is clockwise, and that makes it negative. And the same is true for our last force, which is negative 10 kilonewton multiplied by 6 meters in this case. And so I will find that my MAZ is actually negative something, right? Because if I flip this equation around, like I bring this to the other side, then I have negative here and negative there. And so the ultimate result is negative 114 kilonewton meters. But really what that tells me is, hey, Raphael, you were wrong about your initial assumption and you have to flip it around. So therefore, what did I assume? I assumed clockwise. So it must be counterclockwise. So let's fix that. So therefore, I have 114 kilonewton meter counterclockwise. And that is the real result here. So it deserves an answer error. And I want to talk about one last thing, is that you can actually almost feel this intuitively or see this here, right? So if you think of a needle pointing here into the page and you let the system rotate, right? So pretend that this all here is gone and you poke a needle into the page and you push down here, you push down here. You would intuitively know that you have to rotate back here at this location. You have to rotate this counterclockwise, while this here is turning clockwise. And so you understand almost intuitively if this is correct or not. And in this case, of course, it's correct. It turns counterclockwise upwards. And that concludes this example problem, which I believe is straightforward, and we can now make it a little bit more interesting and look at our next example. All right, so here we have our next cantilever problem, which I believe will be enough to teach us all about the support reactions in cantilever systems. So let's complete this and then move on to our next topic. What we have here is a cantilever that actually has a support on the right side, and there is a force under an angle and an evenly distributed force that is not continuous throughout the structure. So as always, let's go ahead and draw our free body diagram first and copy our dimensions over. So first I have a rigid body. It deserves the dashed line. I have my evenly distributed force that goes over 6 meters here. So I have such a system, which is 20 kilonewton per meter. And then I have two types of forces here, really, that I can break them down into a vertical and a horizontal component. So I have the first one, which is really 100 times the sine of 75, and I have 100 times cosine 75. And that one is acting to the left. Please use that correctly. So I'm going to symbolize it as such. And last but not least, I of course have my support reactions, which I assume to go up, I assume to go to the left, and I assume to turn counterclockwise. And I call this MA about the z-axis. I call this RAX, and this here is RAY. Last but not least, let me get my dimensions so that we don't get lost when we scroll down. So I have this being 2 meters, this being 2 meters, and then this being 6 meters. And now I go ahead and solve the problem for you, or at least as much as necessary. So let's start with RAX. And I do that by the sum of the forces in the x direction being equal to 0. And that is positive to the right. 0 is equal to minus RAX, or maybe better, minus positive RAX. So minus positive RAX. And then minus, and this is really a minus, right? Minus 100 times cosine 75. And what I will find is that this equates to RAX being equal to minus 25.88 kilonewton. And that is not the result, right? Because that means that I made a misassumption here. I said negative. So therefore, it is positive to the right, which makes perfect sense if you think about it. The 100 cosine 75 pulls to the left. And to balance that, I need to use RAX, which then has to pull to the right. Otherwise, it cannot be in balance. So in other words, my RAX is equal to 25.88 kilonewton to the right. And this is really my result. So this I can now double underline and also use my answer arrow. And I can move on to my RAY, which is nothing else than the sum of the forces in the y direction being equal to 0, upwards positive, and 0 is equal to plus RAY minus 100 times sine 75 minus 20 kilonewton per meter. And by the way, this is also in kilonewton. 20 kilonewton per meter times 6 meters. And notice that this completes it already because this crosses out. And now I already have the right unit. And what I will find if I solve this is that RAY is equal to positive 216.5 kilonewton. And that means that it's pointing upwards. I assumed that correctly. So I can make this my answer. And my last result now is the moment, which I calculate by the sum of the moments. So to find MA about the z-axis, I use the sum of the moments about point A in this case. And now it becomes sometimes initially confusing for students because it's the first time that they have to rotate about the other side of a cantilever beam, but you will see it's not that difficult or that different. So I start with my unknown, which turns clockwise. That makes it negative. So minus MA about the z-axis. And let's start with the 100 sine 75. So 100 times sine 75, which of course this is in kilonewton. So we need a lever arm now, right? Because our moment here has a lever arm. So what is that lever arm? That lever arm happens to be 2 meters. So that is the distance from this force to this point of reference. That's the point that I take the sum of the moments about. So let's actually highlight that. So I'm taking the sum of the moments about that point. And how does this rotate? It rotates counterclockwise. That makes this positive. Sorry, is that correct? Counterclockwise positive. Yes. Why was I confused? Because here I used a negative and therefore I was wrong there. So this is actually positive and this is also positive. So please note that I made a mistake here initially. This needs to be negative. Sorry, it needs to be positive. All right. So now I can use my other force, which is also positive, 20 kilonewton per meter multiplied by 6 meters. And now comes the trick, which is not a trick really once you understand it, but you know that the lumped force acts here, so at 3 meters and 3 meters, and we need to take the sum of the moments about this point. Therefore, we need 3 meters plus 2 meters plus 2 meters. So let's write it down as such. So multiplied by 6 over 2 plus 2 plus meters. And let's understand that this is the lever arm. And this is the lumped force. So F resultant is what I usually call that. And just to be 100% sure, let's actually draw that into our diagram here on the top. So I would have a lumped force right here. And my lever arm would be this distance here. And so we're talking about 6/2 plus 2 plus 2 from here to here. And now all I have to do is calculate it out and find that my MA, and again, keep in mind that I made a mistake here initially. I actually assumed this to be negative, but it must be positive because it turns counterclockwise. And this force about this point also turns counterclockwise, and this lumped force about this point also turns counterclockwise. So everything turning counterclockwise cannot be true, right? Because then we would have no rotational equilibrium. Therefore, my answer must be, by all means, negative. And the numerical answer here actually happens to be 1033 kilonewton meters. So what we know is that my M is actually 1033, and that would be clockwise, right? So that is my real answer, or I could also say that it's clockwise, meaning this way, since it's a 2D description. So last thing for me to do here is to double underline it and use my answer arrow. And that completes the problem, because I now calculated all three support reaction at location A is what I called it. And the important thing to understand is that this support resists all three different types of forces and moment, or two forces and one moment. And then that I showed you that now if you have a force under an angle that is resisted here by RAX, which needs to be in balance, that's why we found the negative answer here first. Then we assumed correct RAY, we found that to be positive, and it told us that yes, we have to push up. And for our last identifier, the moment here, we found a negative answer, because you can see that if I equate this equation to MAZ, it becomes negative. And that means that we assumed incorrect, which is of course making sense, because everything turning counterclockwise cannot be true for a balanced system. So therefore we needed to rotate against it, or clockwise, with 1033 kilonewton meters. And that completes this problem, and we are now ready to tackle other distributed force types. We will do that on the next page, and I will see you there.